All right, today we're diving into something truly wild. We're going to explore a groundbreaking study that takes something we see every day, a single droplet of water, and slams it into something most of us will never see: plasma, the fourth state of matter. The result? Well, let's just say it's anything but simple.
So what does happen? It almost sounds like the start of a physics riddle, doesn't it? We've all seen a raindrop hit the pavement. It makes a splash. But what if the surface it hits isn't a solid, or a liquid, or a gas? What if it's this super energized, exotic state of matter? That's the question we're digging into, and trust me, the answer is way more spectacular than you're thinking.
Okay, so here's our game plan. First, we'll look at the collision itself. Then, we'll get into how scientists even make a plasma surface in a lab. After that, we're going to slow things way down and watch the impact millisecond by millisecond, explore the crazy transformation that happens next, and finally, we'll talk about why any of this is a big deal.
All right, Section 1, the four-state collision. This is where our story begins, with this one little water droplet about to have a very, very interesting day. I mean, think about it. It's going to interact with a solid surface, the gas around it, and plasma, all at the same time. This isn't your average splash. It's a full-on dance between all four states of matter.
And right away, things get weird. Instead of a normal splash, the droplet just erupts. Look at that. It creates these beautiful, almost tree-like finger structures. This is our very first clue that something totally different is going on here. There are some seriously powerful and unusual forces at work.
Okay, so to figure out why it makes that incredible pattern, we've got to look at the surface it's hitting. I mean, how in the world do you make a flat sheet of plasma to drop water on? It sounds like something out of science fiction, right?
Well, they do it with a clever trick called dielectric barrier discharge, or DBD for short. Basically, and this is the simple version, you take two electrodes, put a non-conducting material between them, and then blast it with a high-voltage AC signal. What that does is it super energizes the air right on top of the surface, and boom, you've got a stable, thin sheet of plasma. That's our stage.
But here's the thing. This plasma isn't just sitting there looking pretty. It's active. It's actually creating a force on the air, making this invisible current that flows right across the surface. They call it the ionic wind. Think of it like a gentle, constant breeze. And you're going to want to remember that ionic wind, because it plays a huge role in what happens next.
Okay, so the stage is set. We've got our plasma surface, we've got our ionic wind blowing. Now for the main event. Let's look at the exact moment that droplet hits and see how this whole plasma thing just throws the rulebook for a normal splash right out the window.
And this comparison says it all. Look at the difference. Plasma off, on the left, you get a pretty standard splash, right? A few small fingers, nothing too crazy. But now look at the right side. With the plasma on, whoa, the spread is way, way bigger. Those fingers shoot out, getting much longer. And look at the time. It takes more than double the time to reach its maximum spread. The plasma is literally pulling the droplet outwards.
So the big question is, why? Why this huge difference? Well, it boils down to three main things. First, the plasma makes the surface way more wettable, easier for the water to grab onto and spread. Second, you've got these intense electrohydrodynamic forces basically yanking the droplet outward. But the third reason, this is where it gets really nuts. The droplet isn't just a victim here, it actually joins the party.
You heard that right. The water droplet literally transforms. It stops being just water and becomes what's called a liquid electrode. It actually becomes part of the electrical circuit. The charge from the plasma flows right into it, and all that charge builds up at the very tips of those long fingers. It gets so intense that you get little bursts of plasma coming off the water itself. How cool is that?
But that initial splash, that beautiful pattern, that's just the first few milliseconds. That's just Act 1. The story is far from over. After the spread, the whole thing turns into this intense, sizzling battle of heat and electricity that can go on for almost 2 minutes.
So let's walk through the droplet's entire life cycle here. In the first 10 milliseconds, you get that impact and spreading we saw. Then, for the next second or so, it starts to heat up, and you can even see a faint glow at the fingertips. And then things get really dramatic. These high-intensity plasma streamers, think of them like tiny lightning bolts, start to form, connecting the main electrode to the droplet. These things are super hot, and they would eventually cause the whole droplet to just disappear.
And when I say hot, I'm not kidding. The actual physical temperature of the gas, which you'd measure with a thermometer, gets up to around 850 Kelvin. That's pretty hot. But look at the vibrational temperature.
That's a measure of the internal energy, how much the molecules themselves are shaking and vibrating. It hits an absolutely mind-boggling 4,200 Kelvin. That is a ton of energy being pumped into this tiny spot.
So what's the bottom line here? Those plasma streamers we've been talking about, they get hotter than 100 degrees Celsius, hotter than the boiling point of water. So yeah, they are literally boiling the droplet away on contact. That's what drives that final super fast evaporation.
Okay, so remember that nice, steady ionic wind we talked about earlier? That gentle breeze? Well, guess what happens when our little droplet shows up? It throws the entire system into total chaos. The droplet isn't a passive observer. It acts like a giant obstacle, completely changing the plasma field around it and messing up that entire flow.
And this chart really paints the picture. Just look at the numbers. Before the droplet hits, the wind is cruising along at just under an 8-degree angle, pretty much flat. But then, 30 milliseconds after impact, look at that jump. It's deflected upwards to over 43 degrees. That one tiny little droplet is like a giant boulder suddenly dropped into a calm stream, forcing everything to go around it.
So this is all incredibly cool science, right? But you might be wondering, okay, so what? Why does this matter in the real world? Well, let's talk about that. Let's connect this crazy lab experiment to some amazing technologies.
Because if you can control droplets with plasma this effectively, the possibilities are huge. Think about airplanes. You could create these super efficient de-icing systems. Or in medicine, this could lead to next-level sterilization tools. You could use it to treat wastewater, or even to design brand new materials with unique properties. I mean, the list goes on. This is exactly how that fundamental what-if science in the lab turns into stuff that can actually change the world.
And that really brings us to the final takeaway here. All of this entire complicated, beautiful dance of physics, it all started with one of the most common things in the world, a single drop of water hitting a surface. It just makes you wonder, right? How much other incredible, mind-blowing science is hiding in plain sight in all the simple little things we see around us every single day.